Hello everyone, this is just a quick and dirty lesson on Dalton's law of partial pressure. So it looks pretty simple here from the formula. P total equals P1 plus P2 plus P3. And if you look at the examples, the first example on your notes page gives you everything in the same unit. The number one example gives you 0.25 ATMs, which is atmospheres. 1.1 ATM for gas B. Gas C is some number you don't know. I'm going to let X be there. And the P total is 2.0 ATM. The reason this is so easy is because everything's in ATM. So all you do is just add up these two. So when you add these two, you get 1.35. And then you add X to get 2. So the simple math there, X equals 0.65 ATM. So that's when Dalton's law is really simple. But let's use another example where everything's not the exact same unit. So we may have to do some conversions here. So once again, I like to draw out my Florence flask connected to a hose with clamps on them to let the gas in or out. So that's why these little T's are here, so you can tighten down on the hose to block the flow of the gas. But first of all, we'll start off with something pretty easy here. We'll say that P total is, just to make the math easy, 10 ATMs. We'll just neglect sig figs for this short training. Now, look, what if your gas A happens to be 1520 millimeters of mercury, and gas B is 202.6 kPa. Then you had to find X in ATMs. Ooh, this is a lot different than that first problem, isn't it? But if you know your conversions, you just simply convert all of them to ATM. So remember the 1520 millimeters of mercury. If we use our factor label, that's 760 millimeters of mercury. That's from last week's lesson, is 1 ATM. That makes this simply 2 ATM. Wow, that makes it a lot easier there. What about gas B? 202.6 kPa, and we look back and see that 101.3 kPa is 1 ATM. That also is 2 ATMs. So just to make that easy, we've got 2 plus 2 plus some number we don't know equals 10. Obviously, gas C, X equals 6 ATMs. All right, that was really simple. Be sure that you look at the picture that I'm going to send along with this to show you what these actually look like connected to a hose with T-clamps. What if we had another picture where we had a glass tubing and it looks like water is being suspended in that gas tubing? Well, that's also where you have the air pressure holding up water inside of a tube. If you want a real-life example of this, look at an automatic feeder for cats or dogs. The water is being held up. Looks like it's just being suspended up in the air in something like a 2-liter bottle. Okay? So we're going to look at this equation is nothing more than P total, your pressure of your total system, equals your P of your gas, the pressure of your gas, plus the pressure of your water vapor. Now you're thinking, what's this water vapor? On the back of your notes, you'll see a whole chart that says vapor pressure for water. Now you have to have a temperature, so I'm going to write that over here. Must have a temperature in order to look up the water vapor. Once you have that and you know your P total, you just subtract. Because how would you find X here? You would subtract the water vapor. So the first example you had there was nothing more than you find the P total of 93.5 kPa. This is example 1. You don't know the pressure of the gas, but you know that P vapor, you look it up from 13 degrees Celsius on the chart and you see that is 1.5 kilopascals. So how do you solve for X? You just simply subtract. So I'm going to subtract that out and get 92, I should say X equals 92 kPa. All right, we'll do one last one here. The second example we had a total pressure of 207.33 kilopascals. You're trying to find that gas, and you look up the temperature this time, and it's going to be 3.36. A lot of kids just memorize it. When you see water vapor, you just subtract it from your total. And that's a simple way to remember it. So your final answer here is 203.97 kPa. Hope you enjoyed Dalton's law of partial pressure. Be sure to look at the examples of the pictures I'll send as well.